Okay, welcome to discussion. And as I mentioned, I think last week, we're going to actually talk about chapter one today, just to make sure we talk about it. Again, as I mentioned earlier, there's not a lot of per se chemistry in there, chapter one, but, and again, please also put here in the chat for discussion as well. But, there's some stuff to talk about, and some stuff obviously we will come across in a later chapter as well. And there's also some nice math review towards the end of chapter one, a little bit about scientific notation, which we've talked a good amount in lecture as well. So, and I think there's even a section from chapter one about studying chemistry and those type of things. So you may want to look at that stuff. You are responsible, obviously, for chapter one and some of the stuff that we're talking about today. But I would say probably the heart of sort of chemistry and really starting the material is chapter two, which we've been working on. But I did want to kind of go back and sort of formally maybe talk about some of the stuff that we do see here in chapter one. And like I said, we'll probably see a little bit more on some of these topics a little bit later on in some other chapters as well. So again, these lecture notes are up there on Canvas. I believe they're all filled in as well, but we'll just touch upon some stuff. And again, we might have already touched upon some of this stuff, but we'll just kind of reiterate some of the important aspects, obviously, of what's sort of in chapter one. So obviously, so a little bit about introductory, obviously, to chemistry and so forth. You know, things chemistry really does touch all aspects of life, from just regular sort of science, if you will, chemistry, biochemistry type of science, things like forensic sciences, food science, right, has chemistry involved, things like makeup, shampoos, all that type of stuff, involves aspects of chemistry. Obviously nutrition as well involves chemistry, so it really does sort of come across in a lot of areas of life that we see, even things, obviously, there's chemistry involved in proteins and how they sort of interact with each other, amino acids in the body, how bonds occur between those things. So oftentimes when we talk about chemistry, a lot of times we focus in on sort of matter and sort of how matter is changed from maybe one form to another. So, just kind of a basic definition of matter is basically anything that has mass, basically, and occupies space. So, pretty much anything around could be solid, could be liquid, could be gas. These things are basically considered matter. And a lot of what we look at in chemistry, as I mentioned, is sort of, what happens with matter as it undergoes changes, as it reacts, or maybe as it doesn't react, is resistance to reactions. And, what happens in terms of things like energy as these things are occurring. Is energy being given in? Is energy being given off in these processes? So these are very common things that we look at when we're studying chemistry. One important sort of thing is, like I mentioned, matter and really the different sort of states of matter. So when we talk about matter, there's really three sort of states of matter that we oftentimes will deal with. And again, in a later chapter, I think maybe chapter three, we'll go more into detail on this stuff. But, there's solid state. There's basically liquid state, which is abbreviated with an L. And there's the gas state, which is abbreviated with a G. And when we talk about sort of those things, when we talk about things in a solid state, for example, we're usually talking about things that are packed in relatively tight to one another. There's not a lot of room for movement. And that's why when we think about things that are in the solid state, they're very rigid. For example, maybe the desk you're sitting at right now, the table you're sitting at, it's fairly solid. It's not very easy to change the shape of it. And it has a lot to do with how all those sort of chemicals and molecules are all packed into each other. When we get to the liquid state, we still have things that are relatively packed into each other, kind of close, but there's a little bit more room for movement. And that's why when we think about liquids, we oftentimes think about them as being fluids, right? And that's because really the molecules and the atoms are able to kind of move past each other, and that gives really the liquid state that more fluid state that obviously we think about when we have some type of liquid that's present. And lastly, when we get to sort of the gas state, we pretty much have reached a state where everybody has 100% basically broken apart from each other. So they're flying around, they're moving around, they're actually colliding with the container they're in. And that's what we associate with pressures. For example, when we get to the gas chapter, that's basically what causes pressure that's associated with gases. The more collisions, the more things they run into, the more pressure that we basically have. And so when we talk about, matter and chemistry, we think about the composition, what is it made of, sort of how it's put together, different properties that different things have, and really how they react with one another are very common sort of topics that we talk about in chemistry. Just to sort of finish this little talk here about the different states of matter, one important thing we oftentimes will look at is sort of what happens as we go from one state to the next. So when we go from something from solid to the liquid state, that's usually known as the process of melting. If we go the opposite, where we go liquid back to solid, that's usually the process of freezing. When we go from liquid to gas, that is the process of evaporation or vaporization. Going from gas back to liquid, that is the process of condensation. There's also a process where we actually go from solid and we skip the liquid altogether and just end up over there in the gas state. And that is what is known as sublimation. Perhaps you've seen dry ice before. That goes through sublimation. Dry ice is really carbon dioxide. It's not really water, even though we call it ice. It's actually CO2. And there's also the process where we go from gas back to the solid state, and that is what is known as deposition. So these are common sort of changes of state that we deal with a lot in chemistry. What's happening as we go from one state to the next, also what's happening in terms of something like energy as we actually go from one state to the next. So for example, if we went from solid to liquid to gas, in terms of energy, you would have to put energy or heat in to do that. So if you just think about a pretty simple example of that, we have to put heat and energy in, and that's what's sometimes referred to as being endothermic. So endothermic is when we put heat or energy in. But a simple thing like an ice cube, right? If we have a piece of ice and we take it out of the freezer, for example, it pretty much will pick up all that heat and energy from the surroundings, and our poor ice cube, right, will start to melt into like liquid water. And then maybe if we gather up that water, put it on our stove, because it seems like a good idea to make pasta right about now, we could heat it up, right? And as we start to heat it up, and we will start to see it boil, right? And as it's boiling, we'll start to see steam, which is basically the water going into that. So all that process requires energy to be put in and heated, and that is what is known as an endothermic process. Opposite of that, if we were started at gas and actually went to liquid to solid, heat and energy would need to be removed. And that's what's known as exothermic. Exothermic. And we could start with, for example, our gas molecules as they're flying around. If we kind of cool them down, they're not going to be flying around as fast or have as much energy. And what's going to happen is as they fly around, they're going to kind of come in contact with each other. They're going to kind of stick. So they're not going to be able to escape each other. And as they sort of stick, they're going to fall back into the liquid phase. And if you continuously take, for example, liquid water and you throw it in the freezer, that's like removing a lot of heat and energy. That liquid water, right, will freeze back up to our full circle here, back to our ice cube. And that's obviously in the solid state. So again, in terms of chemistry, matter how it's changing, what's happening with it is a lot of things that we really do sort of deal with and look at. As I mentioned before, again, matter is basically, pretty much everything. The process of liquid to gas is the process of evaporation, or sometimes referred to as vaporization. So evaporation or vaporization is going from liquid to gas. So like when something evaporates off, right, or water evaporates. So that's sort of the process known as that. So matter, again, is pretty much everything. And as we can see here, some examples, obviously, of matter. Something could be an antacid tablet, right, which would have obviously the solid state. Water is the liquid state. Oxygen is actually gas. By the way, oxygen comes as O2. The way oxygen naturally comes is two oxygen atoms basically bonded together, like so. Hydrogen also comes that way. Hydrogen comes as a gas, as H2. Again, two hydrogen atoms basically bound together, and that's how they naturally come. Chemicals are essentially substances that have the same composition and properties no matter where you find them. Obviously, there's lots of chemicals and things. Looks like they chose toothpaste there. So obviously, toothpaste has a lot of different chemicals in it. But when we talk about chemicals, something like a substance, for example, can be something like water is a substance. And if you just have pure water, it is H2O is the formula of water. And the little number on the bottom goes to the element to the left. So that means there's two oxygen atoms for every one, I'm sorry, I say that right, two hydrogen atoms for every one oxygen atom that's present. And we have something like CO2. We're talking about dry ice. So CO2 has one carbon atom for every two oxygen atoms. So no matter when you do it, you would have two carbon atoms for every, I keep saying it backwards, huh? That's the end of the night, I suppose. One carbon atom for every two oxygen atoms. There we go. So when we look at this is what's referred to as a chemical formula. If there's nothing written next to the element, it's assumed to be one. We oftentimes in chemistry don't write ones for a lot of things. So if you don't see a number, it's usually assumed basically to be one. So no matter where you find something like water, it's always going to be those two hydrogens for one oxygen. It's always going to be basically this arrangement. May cost more depending on what bottle they put it in, but the fundamental part of it is always going to be the same. It's always going to be basically that H2O that's together. This is a table, I think, from your book describes the different chemicals, and obviously different chemicals can have different functions, and basically the way they react as well is a very big part of chemistry. And there's some of the common ones found in toothpaste, for example. Which of the following contains chemicals? Pretty much everybody there contains chemicals except for the sun, right? So sun is basically just kind of pure energy, but everybody else would have uh, some type of chemicals involved in there from, say, citric acid, for example, milk, lactose, breakfast cereal has a lot of different chemicals sort of involved. Yeah, to be honest with you, I'll let you know for sure next week what the quiz is going to be on. But honestly, I think it's just going to be on chapter 2. It'll probably just be the quiz. So when we look at these again, there's chemicals and all these things, but really sun really is all about energy, pretty much, not too much. Sunlight, for example, or the energy can be used to actually help certain chemical reactions occur by providing the right amount of energy for that to do it. Now, there's sometimes two words that people sometimes have problems with or maybe get confused. And those two words are molecule and compound. kind of what is the difference between, say, these two things. So I guess before we could get to those two things, we should talk about elements. Elements are basically, sort of like the alphabet, right? There's only 26 letters in the alphabet. Yes, this will be uploaded up online when we're done. Elements, just like the alphabet, there's only 26 letters, but right, different combinations give you different words. Same thing with our elements. Elements are sort of our basic building blocks here, and different combination of elements, different amounts of elements will be give you different molecules, may give you different compounds, really different compounds. The basic unit of elements obviously can be found on the periodic table, like hydrogen, oxygen, and so forth. But the basic unit of elements are atoms. And atoms, as we'll talk about in a later chapter as well, those are the things that contain protons, neutrons, and electrons, which we'll obviously talk about in a later chapter. So your basic sort of unit of any element are atoms. Now, when we talk about the combination of two or more atoms, that is basically your definition of a molecule. So when you put two or more atoms together, those could be atoms of the same element, they could be atoms of different elements, but just simply a combination of two or more elements. When we talk about a compound, it's actually a combination of two or more atoms from different elements. So you may say that kind of sounds very similar. Are they not the same? And they're actually not the same. So a very good sort of way to look at this is you could have something like O2 that we just saw, H2, I2, for example, Br2, Cl2, and so forth. We got there, Br2, I2, F2, N2. Now, all of these are basically two atoms of an element, like oxygen that I drew a second ago. But they are two atoms of the same element. So they are two atoms, which means this is considered a molecule. But because these atoms are the same element, they are not a compound. They're actually still an element. These are what are sometimes referred to as diatomic molecules. Basically, have two. Now, if we take something like we saw before, which was CO2, that is basically this combination, a carbon attached to two oxygen atoms. This is a molecule because you know what? It does meet the definition of at least two atoms together. This is also a compound because it's two atoms of different elements. We have a carbon and we have oxygen involved. But CO2 is not an element because it is more than one element there. There's both carbon and oxygen. So a molecule can be a compound, a molecule could be an element, but an element cannot be a compound because it's the same element, obviously. So that's the major difference between those two. And again, we'll talk more about it when we get to a little later chapter. Water as well is a molecule because it's two or more atoms. It's also a compound because it's two or more elements there, hydrogen and oxygen together. Water is not an element because, again, there's more than just one element involved, hydrogen and oxygen. Any questions on that there? Okay, so it's a little preview of that conversation. So let's talk a little bit about the scientific method, which they also talk about here in this first chapter. The scientific method really all starts with a lot of times an observation. So a lot of times you observe something that happens, and obviously it might interest you, hopefully, and you may say to yourself, oh, that was interesting. Why did that happen? So what you try to come up with is a possible explanation for why that happened, and that's what's known as a hypothesis. Usually a lot of times a good hypothesis is something that can be tested. So perhaps you could run an experiment if we're talking about something with chemistry or something like that to see if you see that observation again. Now, it's a testable sort of explanation of what's happening, which means you then can run experiments. And usually this is what leads to maybe a vicious sort of loop. Usually when you do the experiment, you make more observations, which maybe leads to more hypotheses and leads to more experiments. So it can sometimes turn into a vicious sort of loop, the scientific method. And sort of in diagram form here from your book, that's what we see here. We have our observations. We come up with an idea as to why that happens. We test it. Perhaps we get more observations, which leads us to more hypotheses and so forth. And at some point, perhaps we end up with either a theory or a law of what we are sort of seeing there. And there is sort of a difference between those two. Basically, a theory, for example, is something that may be thought of as being correct, but may later be shown maybe it's not correct at all, or maybe parts of it's correct and other parts are not so correct. So, for example, there's something known as Dalton's atomic theory, and it's correct in a lot of what it sort of discovered, but there's parts of it that is definitely incorrect that was later proven not so correct as more experiments were done. Something known as the Bohr theory of the hydrogen atom, same thing. It worked really well for hydrogen, but as more people did experiments, they said not so great on things other than hydrogen. So theories in general can be something that works very well for things, but may be sort of found to be later not so correct in all aspects. And that's different than a law. When we come up with a law, that is something no matter what the situation is, or sort of has been proven over the time that it always will happen the same way. So what that means is, for example, the conservation of energy. So we have the same energy. We don't lose energy. We don't create energy. Energy is just sort of moved from one spot to the next. Same idea with the conservation of mass. If we start with a certain amount of elements in a reaction, we'll end up with the same amount at the end. So there's that conservation of mass, and that's a law that always sort of happens. So a theory, again, is something that, maybe correct, but maybe not correct in all aspects of every situation. A law sort of correct in every situation, not really ever proven to be incorrect in that case. Again, sort of the book example here, I'm assuming she's itchy and not feeling good because of the cat. Sad cat. And so perhaps your hypothesis is the person is allergic to cats. You could test it obviously by either bringing the cat towards the person, which I guess would be a mean thing to do, or have the person leave the area where the cat's at. Obviously, if stops itching and sneezing, perhaps your hypothesis was correct. If she's still doing, maybe your hypothesis is incorrect. She's still having those symptoms away from the cat. Could also perhaps bring her to another cat and, kind of see what happens in that situation as well. And again, that's a place where you can make an observation, maybe revise it and take her to more cats and kind of see what happens with it. And that's sort of what this says here. All right, so I think that's good for here. We'll skip some of that, I think. All right, let's talk a little bit about math skills. And again, this is part of it. And just a couple reviews, some, basic sort of math stuff that you're probably familiar with. But again, in case you're not, it's a good idea to maybe to look it over in chapter 1. They do go over some of these, sort of math skills. Again, just location of places, obviously, thousands place, hundreds, tenth, and ones place. Again, these are important to maybe identifying where a significant figure might be. We also have our decimal places as well. There's our ones, our tens, hundreds, and thousands place going through. So, hey, the significant figure is the tenths place, which would be here, obviously, or maybe it's the hundreds or the thousands, and be able to identify those correctly. So again, if we were to look at something like this, we can see that we have our tens place, our hundreds, tenths, and hundreds place here. Again, our different decimals. And remember, you do want to make sure that you put things in the right significant figures to the right number of places. You don't want to drop off any numbers like we talked about as well. Basic sort of math operations, right? Positive, negative. Usually we don't write the positive like this, right? So if it's a positive number, we definitely don't put it usually. If it's a negative number, we do put it. So you want to make sure you do that. A reminder that if you multiply, for example, a positive times a positive number should give you a positive number. If you take a negative times a negative number, will also give you a positive number. And if you take a negative number times a positive number, that will give you a negative number. So um, remember, in terms of multiplications, if you have some negative numbers involved, make sure that you keep that in mind, that you end up with the right sign or the correct sign of what you're looking for. Here again, a couple of examples. We got 2 times 3, which is plus 6. Again, we typically wouldn't put the plus. And we have minus 2 times minus 3. Again, those two negatives will turn that into a positive number. And again, obviously, we would report it as just 6. And a positive and negative, as you can see, negative on each of those gives you numbers. Also, when we divide, same thing. 2 positive numbers give you a positive. 2 negative numbers will give you a positive number. A negative and a positive number will give you a negative number when you divide it. Speaking of division, it's important when you give answers that you actually do the division. So don't give an answer like 1/4 as your answer. Actually do the division and give me 0.25. Otherwise, I think you're too lazy to do it. Not for that, but I have had people in the past go, hey, the answer is 325 miles per 1,253 hours, and just put a circle over it as the final answer. Again, don't leave an answer like that. Make sure that you divide it out and get sort of a number, a decimal type number or something like that. And again, we talked about that. And again, you don't have to put the positive number, obviously. And obviously, if we add and to a negative number, positive and negative, basically you're multiplying, which basically turns that into minus 15, essentially, right? And that gives you minus 3 that's happening in that case. Here's again some more examples. And again, if this is something you need to review, chapter 1 does have it. I almost think maybe on Master Chemistry there might be a math thing. I'm not 100% sure. I don't remember. But make sure you do that. I think we talked a little bit about our calculators in lecture and stuff like that, and also in here as well. I think the other time for discussion, but a reminder on your calculator, you want to make sure you're using the right buttons. Again, this is commonly what a lot of our negative buttons look like on calculators. They also sometimes will look like this. We also talked about the importance of our exponent button, right? So a reminder that on most people's calculators, there's usually 3 choices for your exponent button. Again, that EE button, that EXP button, or again, if you have sort of a newer one, you may actually have a button like that. So when we're doing anything in scientific notation, you do want to make sure that you use the appropriate button. Remember, if your calculator has this button, it probably also has like a little circle dial somewhere on it towards the top. And that's usually the ones where you do have to put parentheses around everything. Otherwise, you will end up with the wrong answer when you're punching something in scientific notation. Remember that when you hit that exponent button, it represents the times 10 part of the number. So when you hit that EE button or that EXP button, that represents that type part of the number, which means you do not need to use the multiplication button when you're typing in. Or on this calculator, I can kind of see it here, the shift button and the log button. You should not be using those buttons to do scientific notation. Again, you should be using your exponent button. And I think on this one, I almost want to say it's like right there. Actually, it's right here. So again, just some different ways to punch those in. And I talked a little bit about it today when we're talking about conversions, but it's a very common problem, surprisingly. People have problems punching things into their calculators. So again, if you have a problem where you're taking, say, 425, you're going to multiply it by 12 and then multiply it by 32. And then you need to come back and divide it by 123 and divide it by 22. Again, people always want to kind of put it all into their calculator all at once, and they usually will end up with the wrong answer. Again, as I talked about today, on top, you pretty much can multiply all the numbers you want. So if I were to put this in my calculator, I would hit 425. I would hit the multiplication button. I would hit 12. I would hit the multiplication button. I would hit 32. I would hit the equals button. That would take care of the entire top part of the calculation. Then I would come here and know I'm going to divide by this number. So then I would hit the divide button and I would hit 123. And this is where people get into problems. They want to throw the next number in first. To be safe, I would hit equals and then hit the divide button one more time and divide it by that final number and then hit equals. So again, if you sort of do that division one by one there and hit equals in between, you usually will get the right answer every time. If you try to put it all in at once, and again, you're not maybe familiar as how to do it properly, or you don't do the parentheses correctly, you probably will get the wrong answer. So if you see yourself giving the wrong answer in a situation like that, try this approach where you divide each number once and hit equals, and you usually will be okay. We talked a little bit about it today in terms of percentages, and that's a very common thing. So usually, as we talked about today as well, assume 100 of something, and that just keeps the numbers really easy. You know, again, as we saw today, if you were 57% by mass, that basically means, we'll say it's sodium chloride. That means that you basically have 57 grams of sodium chloride and say 100 grams of the solution. And that's a conversion factor, so you could do it the other way as well. 100 grams of the solution is 57 grams of sodium chloride. So that's a very common thing. Again, like if you got 50% on your exam, hopefully not. It basically means you got 50 points out of 100 points, right? That's the same idea. And again, you could turn percentages into usable conversion factors, much like we talked about today. Something like this, for example, allows you to really solve for a lot of problems. Again, same idea here. 5% red balls basically means if you assume you have 100 total, you have 5 of them that are red in color. Same thing if you have 50% green, basically you got 50 green balls for every 100 that is there. So really important. Again, a lot of times people get confused with the percentages when they're trying to do the math. So we just kind of convert it into usable numbers in that sense. Sometimes it's a lot easier to sort of do. In addition, we do solve a lot of sort of formulas, for example. So being able to solve for things, it's really like opposites as well, just like conversion factors. So whenever you sort of move to the other side of the equal sign, you pretty much want to do the opposite function. So we basically want to get the 8 to the other side. It's plus 8 here, which means the opposite function would be minus 8 to both sides. And if you do that, you get 2x is equal to 6. When we look at the 2x, that's essentially 2 times x, right? We're basically multiplying. So to get rid of the 2 on the left-hand side, we need to divide it to the other side, right? And those guys cancel. That gives us x is equal to 3. So rearranging formulas is something that we do a lot in chemistry. Being able to solve for one variable versus another is really important. And really anything involves sort of equal signs, it's almost opposites. So it's always opposites gets you sort of what you need. Another example here, that's a gas law sort of equation or formula, and maybe you need to solve for something in particular. So let's just say, for example, we wanted to solve for V2. So we wanted to solve for this guy. Although the way it's written, it's not really written as a fraction, but you can kind of think of it like that. Like this is over 1 is equal to P2 V2 over 1. So really, if I wanted to solve for V2, I need to basically move that P2 to the other side. And if we kind of look at it this way, it's up on top. When I move it to the other side, it will end up on the bottom, and we will end up with P1 V1 over P2 is equal to V2. Ultimately, what we're really doing here is we're doing opposites. So we have P1 V1 is equal to P2 V2. We're basically dividing P2 times V2. So we're going to divide to both sides, basically, is what we're doing. And we end up with the same thing here. We may even have multiple variables all over the place on top and bottom. And let's just say in this case, we want to actually solve for P2. And this is actually a formula we'll see later on in the gas chapter. And again, you could take the simple approach of move things to the opposite side. So if I want P2 all by itself, I need to take V2, and it's up on top. It needs to end up on the bottom. And T2 is on the bottom. As it moves across, it ends up in the opposite location. And that leaves us P1 V1 T2 is divided by T1 V2, and that equals P2. So that's sort of a quick way, especially if you're rearranging formulas across an equal sign. Basically, you're going to move things to opposite spots as it goes across the equal sign. It goes to the other side and gets basically divided. Any questions on that? So again, if that's something that you struggle with, sort of formulas and rearranging, we will have some along the way that you need to do. You want to think about how to properly do those things. If it's easier for you, sometimes it's easier for people if they have numbers just to really just kind of throw the numbers in and not think about rearranging, and it's perfectly fine to do. You could just put them in and sort of do it on your calculator and do it that way. But it's good to know how to properly rearrange these things. Graphs, we probably honestly won't be doing too much graphing in here, I don't think, but it does talk a little bit about graphs and how to interpret graphs. But again, we probably won't be doing too much with that. Scientific notation, we did talk a good amount about scientific notation the other day, but just to reiterate a couple of things about it, it has a general form of n times 10 to the n. And remember that this number here is a number between 1 and 10, so not 10 and above, not less than 1. And the goal really is to move the decimal point until we get a number that's between 1 and 10. And depending on which way we move it, we may end up with a positive or a negative number here, depending on sort of which way we go. So if we had 3225, we would assume that the decimal point would be here. If we went one place, that would be 322, which is too big. We go one more place, that's 32.2, which is still too big. Go one more place, gives us 3.225 times 10 to the 3. It's a big number, so it's a positive exponent, and we also moved it to the left. So that's why we ended up with that. If we had a number like 0.001332, if we move it one place, we're at 0.01, which is not 1. Move it one more place, that's 0.1, which is not 1. Move it one more place, that is going to give us a number between 1 and 10, which is 1.332 times 10 to, I lost track there, 1 to minus 3. Again, minus because we went to the right here. It's a small number. We also talked about the idea that when we use a number in scientific notation, all the numbers before the times 10 part are significant. So this has 4 significant figures. The original number also had 4 significant figures. So we never want to lose significant figures as we go from decimal to scientific notation. Same thing here. This guy also had 4 sig figs. This one also ends up with 4 sig figs. The nice thing about, for example, scientific notation is you could actually use it to get the right number of sig figs. And sometimes that might be the only way you could get the right number of sig figs in an answer. So, if I had something like 1.2 and I want to write it as 2 sig figs, or not 1.2, but we'll do something like 1.2 times 10 to the 2, which, by the way, is one place, 2 places. Put a 0 and it's 120 basically, yeah. And if I want to write it with 2 sig figs, I could write it like this. That has 2 sig figs. If I needed the 120 to have 3 sig figs, I could write 1.20 times 10 to the 2. That then would have 3 sig figs. If I needed, for example, 5 sig figs, I could write something like this, and that would then have 5 sig figs. So a nice thing about significant figures, our scientific notation, is you could kind of use it to control the number of significant figures. And if you need it to a certain number, you could basically manipulate it to get you the right number. And again, this just demonstrates not losing sig figs along the way. Again, going 1, 2, 3, 4, 5, 6 places, -6. Again, one significant figure, one significant figure. Same thing here, going 1, 2, 3, 4, 5 places, hence the 5, and also one sig fig and one sig fig there. Any questions on that? Okay. And again, a couple of things there, like we talked about, we got our number between 1 and 10. And again, that would have 2 significant figures. And moving it to positional notation, which is sometimes referred to, or decimal form is here. And again, you do need to be able to write it both in sort of decimal form and convert it to scientific notation as well. And again, you want to make sure you don't lose any significant figures along the way. Here's just multiplying some of those guys. And some of the stuff we talked about here is different ways. And again, really the purpose of using scientific notation, right, is clearly if we left it in sort of non-scientific notation, there's a lot of zeros along here. We most likely would lose some along the way. So a good thing about scientific notation is you might not lose any zeros along the way. This only has 2 for all those zeros, which again is why it has 2 when it gets to there. Again, just some other formats and scientific notation, which we talked about. Again, more importantly, almost like we talked about for a while, making sure that you know how to properly punch these into your calculator using your exponent buttons. And again, this is typically what you'll see when you punch that exponent button in. If you have kind of a display calculator, usually you'll put that E. Again, when you see that E on the page or your calculator, it does represent the times 10 part of the number. And again, that's why they just put 6 at the end. Again, use your negative button, don't use your subtract button, and you should be okay. Again, if you're still having issues with it sometime, make sure you talk to me during discussion or something like that. We can figure it out again on your specific calculator where your exponent button is. If you're not sure, we could probably figure it out. And again, just some more examples how to properly sort of punch it in. Also a reminder that your calculator probably won't give you the answer in scientific notation if you didn't program it to do so. And it also probably won't be giving you your answer to the right number of significant figures either. So just remember that the answer you see on your calculator, although the value may be correct, it may not be the correct way to give the answer for a problem based on significant figures or something of that nature. Again, if you want to turn your calculator to give you your answers in scientific notation, this is one way you could do it. A lot of calculators have like a mode button, and you could move it to SCI. And what that'll do is put all your calculations into scientific notation. A reminder, if you do that or you get an answer in scientific notation, sometimes people will get an answer in their calculator like this. And at the very end, there's like an E -4, or maybe even at the very end, there's like a very small 10 and like a -4 up here. And it's very common people will just report the first part and forget about this part of it. So don't forget about that part because that is an important part of the answer. And when you give the answer on paper, you should not write something like 5.2 E -4. You should write it as 5.2 times 10 to the -4 when you're given the answer, even though it may give it to you like that. And it's sort of an accepted way of doing scientific notation, but it's really not an accepted way when you're writing it as an answer or reporting it as an answer. You should write in proper scientific notation, which is that, and not using the E. Any questions on that there? So again here, if we write each of these into proper scientific notation, we'll go back here. We should go 1 place, 2 places, 3 places, 4 places. This should be 6.4 times 10 to the 4. Only 2 sig figs here, which is why we have only 2 sig figs here. Again here, 1 place, 2 places gives us 2.1 times 10 to the minus 2. Again, 2 sig figs here and 2 sig figs there as well. And again, negative exponent because it was a small number, positive exponent because it was a larger number. And the correct scientific notation for each of these ones here. Again, looking at this, it really has only 1 sig fig. We do want to go 1 place, 2 places, 3 places, 4 places, 5 places, 6 places. So it should be 8 to the minus 6. Again, positive 6 would be a big number. It's minus 6. And that is not correct scientific notation because this part is not a number between 1 and 10. So that would not technically be correct scientific notation. Coming this way, we got 1, 2, 3, 4, 5, 6, and 7 places. Now give us 7.2, also 2 sig figs here. So 7.2 to the 7 looks like this would be the right one. Again, 72 is not a number between 1 and 10. 7.2 is right, but negative 7 means it's a small number, which that obviously is not. So that one would not be right as well. Any questions on that one there? All right. That actually does wrap up chapter 1. Any questions on that? Like I said,